Good morning. This is the continuation of our Unit 3 nuclear reactions. So, in the last class, we have discussed about the way of representing a nuclear reaction and the various conservation laws. Now, today we will learn about what is meant by the Q value of a nuclear reaction. This is something what we have already learned in our lower class by the basic equation C mx c square plus tx plus ma c square plus ta is equal to my c square plus ty plus mb c square plus tb. Here the t etc. represents kinetic energy. Then m actually stands for the rest mass, and here we define the q value or the reaction q value as initial energy minus final mass energy. Okay, so this stands for the reactants, and this stands for the products. That is kinetic energy of reactants and mass of the reactants. This is kinetic energy of products and mass of the products. Okay, so this reaction q value here is the definition is initial mass energy minus final mass energy. It is represented by this equation, that is mass initial mass minus mass final c square. See, this mass initial is actually mx plus ma, this one mx plus ma, then minus mass final, that is my plus mb. So when we take the minus sign inside, it will become minus my and minus mb. Okay, so we can represent this q value of the reaction as q is equal to uh, like this one in terms of mass, and in terms of kinetic energy it is represented as T final, that is final kinetic energy minus initial kinetic energy, which is nothing. From this equation we can write it is Ty plus Tb, that is final kinetic energy, minus this one minus Tx minus Ta. Okay, so now if this q value is negative, and in that case nuclear mass or binding energy is released as kinetic energy of final products. Now if q is less than 0, reaction is called endoergic or endothermic, and in this case initial kinetic energy is converted into nuclear mass or binding energy. Now anyway, the change in mass and energy is related by Einstein's mass energy relation, that is delta equal to delta mc square. That is, any change in kinetic energy of the reacting particles has to be balanced by an equal change in its rest energy, that is Einstein's mass energy relation. Okay, and now so here we have got three equations, 1 2 and 3. Now these equations are valid in any reference frame that we choose. Suppose that the reference frame that we choose is a laboratory reference frame, and in that frame suppose that the target nuclei is at rest, then is at rest. So now if you are trying to, in such a reference frame, if you are trying to define a reaction plane as shown in the figure given here, and suppose that this reaction plane is defined by the direction of the incident beam and outgoing particle, then conserving the component of momentum perpendicular to that plane shows that motion of second outgoing particle will lie in the plane itself. That is, if we are considering a reference frame, say a laboratory reference frame in which the target nuclei is at rest, and now in such a frame we are considering a reaction plane in such a way that it is defined in a direction. The momentum component perpendicular to the reaction plane that we have considered will show that motion of the second outgoing particle, that is thus the motion of the second outgoing particle also will lie in the plane. which is depicted in this figure. That is, the outgoing particles component of momentum will also lie in the plane of the reaction plane that we have considered. Now, conserving linear momentum, that is, here we can see two equations, 4a and 4b. Here equation 4a represents linear momentum conservation parallel to beam direction, whereas 4b represents linear momentum conservation perpendicular to beam direction. Okay, so this cos theta, epsilon and all are marked in this figure. Now suppose that the Q value of the reaction is known, and Ta, that is kinetic energy of the reactants, is also known as a parameter. That is, if Q and Ta are known, then equations 3 and 4a and b represent 3 equations in 4 unknowns. That is already said, and those equations will not have any unique solution. Okay, now they have deduced a relationship between a relation connecting Tb and theta, that is represented by equation 5. So this equation 5 they have plotted in a figure for the reaction, this one, for this reaction they have explained knowledge I am presenting. So here you can see two regions. See here, there is a double sided region you can see, that is, here you can see a figure, and at the same time in this portion itself there is another outcome that is shown in this inset. So this type of behavior is called double region or double region behavior, or this figure is double region. That is, there is no this is a figure, but along with this figure there is some figure that is different, and that figure is represented separately in the inset. So this we call it as a double sided or double regioned figure. Okay, now from this figure they have drawn a few conclusions, and so as it is difficult to remember these degrees and all, if you can remember, you can just mark the x-axis and y-axis, and these degrees also you can mark, and just if you want you can give a rough sketch of the figure. Okay, so this figure is drawn based on this equation 5 for this particular reaction. This equation is represented in this figure for this particular reaction, and from this figure they have drawn a few conclusions, and they are numbered as follows. That is, there is an absolute minimum value of Ta below which the reaction is not possible. This occurs only for Q less than 0 and is called threshold energy Th, which is given by equation 6. Now the threshold that is y and b move in a common direction. That is, no energy is wasted. Now if Q is greater than 0, there is no threshold condition and the reaction will go even for very small energies. That is enough. Okay, now the second conclusion, as I said, we can see a double sided or double valued region there. Now this double valued situation occurs only for incident energies between threshold energy Th and the upper limit given by Ta dash, that is equation 7. Now this also occurs only for Q less than 0, and that become important only for those reactions involving nuclei of comparable mass. So using equation 6 and 7 we can approximate this range as you have to subtract this Ta dash from the threshold energy Th. So you will get an expression like 8. Now in such cases, if A and B have mass numbers of 4 or less, and if Y is a medium or heavy nucleus, then this particular range, that is Ta dash minus Th, will become much smaller than 1% of the threshold energy. Now again that similar graph is plotted for equation 5, but for the reaction this. In the earlier case we have plotted the reaction for another one, and this is for the second one. Here also no need of writing the exact values. You can just give a rough sketch if you need. Now here there is a maximum angle called theta m, that is maximum angle theta m, at which this double valued behavior occurs, and the value for which is determined for Ta in the permit theta m if the term that is given in the square root of equation 5 vanishes. Okay, this term, if this term vanishes, you will get the maximum value of angle theta m, and the corresponding value of cos square theta m is given by equation 9. When both Ta and Ta dash are equal, double valued behavior will occur between theta equal to 0 and theta m equal to 90, and Ta will become equal to Th only when theta m is equal to 0 degrees. Now the fourth point is reactions with Q greater than 0 have neither a threshold nor a double valued behavior, and this you can see in the figure. That is, from the figure it is quite evident. See, here there is no double valued region, that is, there is no figure. They have not shown any figure in the inset. Why? Because there is no such region in this figure. The figure is directly coming like this. Okay, so here there is no doubled valued region. Now for a given value of theta and Ta, we can measure Tb, and then we can determine the Q value of the reaction, and finally we can reduce the mass relationship among the constituents. Constituents means among the reactants and products. Now if we know Ma, Mb and Mx, we have a way of determining the mass of Y, that is a product, and here they have solved equation 5 in order to get the Q value of the reaction, and they have obtained the Q value of the reaction as right. Otherwise you can skip this. They have given it an example of this technique is given, so this slide you can skip because it is just an example showing you how all these points are obtained, and many data values are explained here, so no need of writing about this slide. This slide you can skip. Then now what happens when the reaction reaches the ultimate state, that is the excited state of Y? Then Q value in such cases must include the mass energy of the excited state, and it is given by Q excited is equal to Q naught minus E excited, that is excitation energy. Here Q0 is the Q value corresponding to ground state of Y, and where we have used my star c square is equal to my c square plus excitation energy is taken as the mass energy of the excited state. Now EEX, that is the excitation energy above the ground state. Now the highest value of TB is obtained for reactions that takes place in the ground state, and we can use equation 10 to find the value of Q0 or Q naught. And after finding Q naught, the small values of TB corresponding to higher excited states can also be obtained by measuring TB. Once TB is obtained, we can deduce the Q value of the excited state and the excitation energy EEX. Now this figure shows an example of this kind of measurement. This is also given just for information. This measurement, it actually, what is its use? It actually helps us to find the angular distribution of reactions. or finally angular distribution studies. These are all called angular distribution studies, and this helps us to calculate the spin parity assignments of the excited state of a reaction. And this using this we can draw a level scheme as shown here. So that is one use. Then that is some in some cases we cannot tell which transition connects the ground state with the excited state, and therefore what energies are of the excited state. That means what is the energy of the excited state we cannot predict in some cases. That is in the proton spectrum. It actually gives the excited state energy directly. However, though it gives the excited state energy directly, and then but when we come to or when we come in the case of gamma energies, that can be measured with great precision. We can obtain more precise values for energies of the state. So the main use of this angular distribution studies of nuclear reaction is that it helps us to develop a level scheme from which we can reduce the spin parity assignments of the excited state. So that is the only use of studying these angular distribution graphs. Okay, so here you have to study uh, this one about the q value. This slide is very important. This you have to study, and if you want you can explain it with the reaction plane that they have. It's little bit difficult to remember, but still if you have any way you can try this equation also, because all the explanation starts from this fifth equation. So if you can study, you can study this equation 5. Then using this equation 5, it is predicted in various angular distribution curves for different reactions. One is for this one hydrogen and the other is for carbon. So this you can give a just a rough sketch. See, this is 0 degree, 30, 60, 90, 190, and the only thing is that here you can see a double sided region. Okay, now from this graph what are the things that you can conclude? These points are important: point 1, point 2, then the next graph is also drawn for the other reaction, that is carbon, then point 3, point 4. Okay, now in the last case here they are not showing any double sided region. So up to equation 10 these slides are very important. This you can skip, this one you can include because this is easy to learn, and this one you can skip, and this one just write one or two sentences, that is what is the use of this angular dispersion studies. That is you can write this is enough, that is angular dispersion distribution studies actually help us to develop a level scheme from which we can reduce or from which we can calculate spin parity assignments of excited states included in a nuclear reaction. That is enough. Okay, thank you.